Galaxies and the universe. Today we are going to take notes on galaxies in the universe. Go ahead and take out a notebook and something to write with, please. Okay, the first page we have is the Big Bang Theory. There's a YouTube link at the very top. This is for you to gain more information and to answer any questions you may have. The Big Bang Theory states how the universe formed. It began as matter in a highly condensed state with high amounts of radiation. That's known as a singularity. This matter exploded and expanded billions of years ago, and it's been expanding ever since. It is evident from redshift of other galaxies, which we'll be talking about in a few moments. The true age of the universe is 13.8 billion years. What you specifically need to know is what the Big Bang Theory actually is. It states how the universe formed. Cosmic background radiation. This is radiation left over from the early development of the universe, and it's landmark proof of the Big Bang Theory. Before the formation of stars and planets, the universe was much smaller. It was much hotter, and it was filled with a uniform glow from its white-hot fog of hydrogen plasma. As the universe expanded, both the plasma and the radiation filling it grew cooler. It eventually cooled to a point where stable atoms could form. They eventually could no longer absorb the thermal radiation, and the universe became transparent instead of being an opaque fog. What this picture on the bottom right is showing you. Okay, I have no idea where I stopped with you all, but this right here is a picture in the bottom right-hand corner. This is what space looks like from a radio telescope. I'm attempting to show you background radiation, which is these little bits of green. Okay, so how big is the universe? In 2003, NASA has a satellite, WMAP. It stands for something that I don't know off the top of my head. It took images of the most distant parts of the universe that could be observed from Earth. This image above shows the furthest we can see using any form of light. The patterns show clumps of matter that eventually formed into galaxies of stars. Now, how big is the universe? No one knows, honestly. No one knows if it's infinitively large or even if ours is the only universe that exists. Other parts of the universe very far away might be quite different from the universe closer to home. Future NASA missions will search for clues to the size and scale of our cosmic home. Redshift versus blue shift. This is a really important slide. This tells how we know the galaxies are actually moving. Now, our universe is expanding. This phenomenon is known as redshift. The color red of the spectrum of each galaxy means it's shifting or moving away. Blue shift means moving towards the Earth. Redshift means moving away from the Earth. The Doppler effect is a change in wavelength of light as an object is moving towards or away from you. And the further away a galaxy is, the faster it is moving away. Anything in yellow on this slide is what you need to copy. Now, this slide right here is showing you something called a spectrum. If we took the spectra glasses and we went outside and we looked up in the sky, we would see something that's similar to this top one. This is an unshifted star, meaning this is our sun. These black lines coming right down, these indicate specific elements within the star. Now, if you look at another star, the one in the middle here, this is redshifted. Now, what does it mean to be redshifted? Look back at those black lines where the elements are. Where's my mouse? There it is. If you compare it to our sun, our star above it, the lines in the middle one seem to be moved over towards the red part of the spectrum. All those black lines have shifted to the red side. Blue shift is the very bottom one, and those black lines that indicate elements, those, if you look, they're actually shifted left, or they're shifted to the blue side of the spectrum. This next slide is another way of seeing it. We have a vertical redshift here on the right, and down here on the bottom right, is absorption lines, or those emission lines from elements from our sun, and then from a cluster of galaxies that are 1 billion light years away from us. And you can see from them, everything is shifted. All these black element lines are shifted to the red part of the spectrum. Which elements are present? We will discuss this one during class. Okay, on this slide, distance, time, and the universe. This is where you need to copy anything that's in yellow. Okay, distance time in the universe. Essentially, it is measured using a light year. And a light year is the amount of time it takes for light to travel in 1 year. As far as we know, light is the fastest moving, I'm going to call it, stuff in the universe. Light is actually made of photons. It travels at 300,000 kilometers per second. So it's very, very fast. Quasars. Quasars are star-like, very bright, extremely distant objects at the end of the universe. They give off radio waves and X-rays, and that's how we know they're there. We are able to take telescopes that literally look just for radio waves and X-rays and all sorts of electromagnetic waves, and we're able to find the quasars this way. We think that they are the oldest objects in the universe. They're the oldest objects known so far, in the universe at least. They formed right after the Big Bang. And by studying quasars, we hope to study the formation of the universe. Okay, this picture here, in the middle, that really, really bright thing in the middle, that is a quasar. And the reason this looks kind of cloud-like and really cool looking is because we're looking at radio waves and X-rays picked up by a telescope, and the two pictures are merged together. So it gives us really, really detailed picture of things that we really can't see. It's invisible to us, to our eyes. Dark matter. Okay, dark matter, when you look up at the nighttime sky, the sky looks dark. And what you're essentially looking at is dark matter. This accounts for most of the mass in the universe, and it's invisible. Now, it might be invisible, so you're thinking, why does it make the sky look dark? Because it doesn't give off, reflect, or absorb any light, and it literally makes the sky look dark. There's a Nova SciShow clip right here at the bottom that I want you to click and go ahead and watch that video, please. Okay, so what's our universe made of? There's a little bar graph, or circle graph down here on the right, pie chart, I guess, that you can copy that if you'd like, or you can copy what's in yellow on the slide. Either one, it doesn't matter to me. Okay, data that we've collected so far tells us that all of the universe so far only contains 4% atoms. And atoms are literally the building blocks of stars and planets. Dark matter, remember, it's what makes the sky dark. This comprises 22% of the universe. Now, dark matter, remember, it's different. It doesn't emit or absorb any light, and it's only been detected by its gravity. 74% of the universe is composed of dark energy. Dark energy is pretty cool. It acts as like an anti-gravity. So it's responsible for universe expansion. Go ahead and watch that YouTube clip. Okay, as far as we know, there are two types of universe. There's an open universe and a closed universe. An open universe is expanding forever and ever and ever outward. So imagine like a ball that just keeps getting bigger and bigger and bigger and bigger and bigger, and it doesn't pop. A closed universe, which we think our universe is a closed universe, expands to a point where it can't expand anymore, and then it contracts or pulls back on itself. Imagine blowing up a balloon and then slowly deflating it. That's kind of what a closed universe is, and that, like I said, that's what we think our universe is. Here's pictures of them. An open universe is down at the bottom. You can see it expands outward and outward and outward with no end. A closed universe is up here at the top, where it's sort of like a ball or a balloon, where it starts to get bigger, and it gets to a point where it can't get bigger anymore. And instead of popping, it contracts on itself and goes back to smaller. Okay, black hole. Astronomers are closing in on proof that a supermassive black hole is a source of mysterious radio waves at the center of our galaxy, and our galaxy is the Milky Way. Black holes are objects whose gravitational pull is so strong that nothing, not even light, can escape. Supermassive black holes contain the mass of millions, if not billions, of suns or stars. There is evidence of black holes. There are high speeds of orbiting stars whipping around the galactic center. There's infrared and X-ray observatories. They have detected an energetic outflow from the galactic center and gamma-ray radiation above and below the galactic plane. And I'll explain all of that in class. And we're going to go ahead and stop right here for today. Next class, we will continue the notes.